Okay, so this is the flux property. So suppose that F of XYZ gives the mass velocity of fluid flow at XYZ. Then we can think of the divergence of F as the flux density of F at the point XYZ. So suppose that B is a small box containing XYZ with surface S and volume delta V. Then if we take the divergence of F and we multiply it by that volume, that's approximately equal to the flux of F across S, if F is continuous on an open region containing B. So what this means is that the divergence of F at XYZ multiplied by the volume is approximately equal to the flux of F across the surface. And the approximation gets better as B and delta V get smaller. Thus, if XYZ is the source, so that means like you have a hose in the box, then if we take the divergence of F delta V, that's going to be positive because the divergence is positive and obviously the volume is positive. So the product would be positive and we would have a positive outward flux. So what that tells you is that the fluid is flowing out of the box through the surface of the box and out of the box. And so what that means is that the flux of F across the surface is positive. On the other hand, if XYZ is a sink, then we have a pump in the box at XYZ. So that means that the divergence is negative, which makes the divergence times the volume negative, and the flux of F across the surface is negative. So what that means is that fluid is flowing through the surface and going in the box. All right, so we want to build upon this idea and get the divergence theorem that we're going to be using in 14.8. Not 14.8, but sorry, 16.9. So this is the divergence theorem. So we're going to let G be a simple solid. That means that it has no holes, with surface S having the normal outward orientation. And suppose also that your vector field has component functions F, G, and H. Those are functions of three variables. And that F, G, and H have continuous partials on an open region containing G. Then the flux of F across S is equal to the triple integral of the divergence of F dV. So what this does is it changes a surface integral into a regular volume integral, like what you would have seen back in chapter 15. And so the important thing to realize when you use the divergence theorem is that we can't always use it when we're calculating flux. So one thing you need to have is you need to have a surface that encloses a solid. So if you're calculating, let's say, the flux of a vector field through, let's say, a plane, then you wouldn't be able to use the divergence theorem. You have to use the divergence theorem when you can use it when you have a surface that contains a solid. For example, like the surface of a sphere, or if you have the surface of a closed can, then you could use the divergence theorem, but not for when you have a surface that does not enclose a solid. And so I'm going to let you read the proof of the divergence theorem in the book. Maybe I'll send you a copy of that as well. But what I want to do is I want to get you sort of to intuitively understand the basic idea of it, because it's not really that hard to understand the basic idea that's going on with this. All right, so let's assume that F is a mass velocity of fluid flow, and let G be a box for simplicity. So it doesn't have to be a box, but just to keep things simple and explaining it, let's assume it's a box. and we're going to divide G into M times N times L, smaller boxes, Bij, each with volume delta V, and we're going to let Xij K bar, Yij K bar, and Zij K bar, needs to be a K there, times delta V, be the center of the box Bij, and let Sijk be the surface of Bij. Then one thing that you need to realize is that the surface is the surface of a box, and a box has 6 sides. So each of these Sijk actually has 6 subsides to it, to that surface, that make up that surface. All right, so then when we have our surface integral, this is this triple sum of f dot n ds over each of the m times n times l sides. So we have to add that up. And so, well, wait a minute. So if we have that, then we're going to be double counting some sides here. And so let's think about like what happens with that. So this is equal to this, but this is approximately equal to this based on what we talked about before by using this approximation here. But why is this true? So this is true because the net flux on the inner sides cancel the effect of each other, and we are left with the net flux on the outer sides. So when you have, here's kind of a simple picture here. So let's say we have like all these cubicles here. So we have like, this is a box, and this is a box, and this is a box, all the way along here are boxes. And imagine like we have boxes above this as well. So then when you're talking about these sides, each one of those sides have the 6 subsides. So you have the front side, this side, the back side, the left side, and then the bottom and the top. So you have all those 6 sides. But what happens on these inner sides here? So let's say then the normal, if you're looking at this cubicle here, then the outward pointing normal points out this way. And then if you're looking at this cubicle here, you have minus n pointing this way. So when you're looking at all those sums, if we break it up into the sum of all the 6 sides for each of those Sijk, then you would have an integral for this side with this normal and an integral for that same side with this normal. So let S1 be an inner wall or side, then after opposite orientation pairing, we would have this. So the surface integral over S1 plus the surface integral over S1 with the minus N1, these will cancel because you have the N1 and the minus N1, so they cancel. So what that means is that the only sides that don't cancel are the outside sides, which put together give you the outer surface S. And so, if you look at this one, when we're adding all this up, even though it appears that we're double counting all those inner sides, they all cancel. And so you're just left with this. And so since the net flux on the inner sides cancel the effect of each other, and we were left with the net flux on the outer sides, which together gives you S. This approximation, so the approximation part, this is always true for M, N, and L. So this is always true. The approximation part is here. So this, the approximation gets better as M, N, and L get larger, and taking the limit as L, M, and N go to infinity, we have the formula. And so it doesn't have to be a box, but just for explaining it, it was simpler for it to be a box. And so I think regardless of whether this makes sense to you or not, I think you're going to see that the divergence theorem makes calculating flux much easier when we have a surface that encloses a solid. And you'll see that as we look through some examples now. All right, so let's take a look at our first example here. So we're going to let S be the surface of the unit cube bounded by the planes x equals 0, x equals 1, y equals 0, y equals 1, z equals 0, and z equals 1 with outward orientation. And so we're going to use the divergence theorem to find the flux of F equal to 2x, 3y, and z squared across the surface of the cube. All right, so we're going to let G equal 0, 1, cross 0, 1, cross 0, 1. Which is enclosed by S. Then we're going to have to calculate the divergence of this vector field. So then if we take the divergence of F, remember the divergence of F is the partial of the x component with respect to x. So that's going to be 2, plus the partial of the y component function with respect to y. So that's 3, plus the component, the partial of the z component function with respect to z, and that's going to be 2z. So the divergence of F is just equal to 5 plus 2z. All right, so then if we want to calculate using the divergence theorem, what this would say is that the flux of F across the surface is going to be equal to the triple integral of the divergence of F dV over G, where G is the solid that's enclosed by S. And so what we're doing is we're just going to be integrating the triple integral of 5 plus 2z dV over this unit cube. And so we can write this as an iterated integral. So this is going to be 0 to 1 of 5 plus 2z dz. And then we're going to have 0 to 1 dy and 0 to 1 of dx. And then we can just split this up into a product. So this is going to be equal to the integral from 0 to 1 of 1 dx times the integral from 0 to 1 of 1 dy times the integral from 0 to 1 of 5 plus 2z. And so this would just be equal to x from 0 to 1 times y from 0 to 1. And this one is going to be 5z plus z squared. And so we're just going to have 1 times 6 equals 6. And so that's it. So the flux of F across the surface S is 6. And one thing to keep in mind, if we were calculating this directly, we would have to do 6 separate surface integrals. So we would have to do a surface integral on each one of the surfaces. So if we look at our so we would have S1, S2, S3, S4, and then S5 down in the bottom, and then S6. So to calculate flux directly would require 6 surface integrals, flux integrals. And so you can see this was a lot easier than that. And it tends to be, remember that the Green's theorem is a shortcut. Sometimes polar is a shortcut. The divergence theorem, you can think of it like that. It's really a nice shortcut when you have a surface that encloses a solid. All right, let's take a look at a separate example. So we're going to let S be the surface of the cylindrical solid bounded by z equals 0, z equals 3, and x squared plus y squared equals 4. With outward orientation. And so we're going to find the flux of F equal to x to the 4th y minus 2x cubed y and z squared across S. And so we've got this cylinder and so here we have the z equals 3. And z equals 0 on the bottom. And laterally, we have the x squared plus y squared equals 4. That's the lateral surface. And so let's let G be the solid. Enclosed by S. So there you have G right in there. And then we need to calculate the divergence of F. So let's go ahead and do that. So the divergence of F is going to be partial with respect to x of the first component function. So we'll have the 4x cubed y. And then what's the partial with respect to y? It's just squared is what I meant to have there, squared. So the partial with respect to y is going to be minus 4. Minus 4 x cubed y. So these guys are going to cancel. And then plus 2z. So it only comes out to be 2z. So a lot of times when you're doing these problems, a lot of times the divergence comes out to be something fairly simple, which also makes the calculation easier for you. So then we're calculating the flux of F across our surface. And our surface consists of 3 parts: the bottom, the lateral side, and then the top. But when we use the divergence theorem, we just have to do one triple integral. So this is just going to be equal to 1 volume integral. And so we'll have the divergence, which is 2z dv over g. All right, so since we're integrating a volume integral and it's a cylindrical solid, it makes sense that we're going to use cylindrical coordinates. And so let's go ahead and do that. So in cylindrical coordinates, we're going to have 2z and then times r, and then dz, dr, d theta. And so if we look at this, this is going to be a circle of radius 2 down here. And so our z is going to go from where? From z equals 0 up to z equals 3. And then our r goes from 0 to 2, so radius 2. And then our theta goes from 0 to 2 pi. All right, and so because it's factors, we can split this up as a product. So we can split this up as the integral from 0 to 2 pi of 1 d theta times the integral from 0 to 2 of r dr times the integral from 0 to 3 of 2z dz. And so this first one is going to be 2 pi. So we have 2 pi. Here we're going to have 1/2 r squared from 0 to 2. And then here we have z squared from 0 to 3. So we're going to have 2 pi. And then I'll have times 4 over 2 times 9. And so I'm going to have 36 pi. And so this is your flux of F across S. And so you can see that the calculation was pretty straightforward. And if you were calculating this directly, you have to do three individual surface integrals, and each one may be considerably more complicated than what our calculation here. So this one was, and then we would have to add all those together. So this is a nice shortcut for a problem like this. All right. Any questions on this example? All right, so let's look at a third example then. So we're going to let S be the surface of the solid. G enclosed by the hemisphere Z equal to the square root of 4 minus x squared minus y squared, and the plane Z equals 0 with outward orientation. And so we've got this sphere, and we have this outward orientation here. Now, technically, we probably don't need to be told that it's outward orientation, because whenever you have a surface that encloses a solid, you assume that the orientation is outward unless you were told differently. But sometimes, just to reinforce that, you'll see in the book where they'll say it's an outward orientation, just so that it's not confusing. And so we're going to compute, or in case you may have forgotten that, the flux of F equal to x squared over 2 yz, and then minus xz across S. All right, so the first thing we probably want to do is we want to calculate the divergence. And so what's the divergence of this vector field going to be? So what's the partial of the first component function with respect to x?
X.
X. And what's the partial of the second component function with respect to y?
Z.
Z. And then what's the partial of the third component function with respect to z?
Negative X.
Minus x. And so the divergence of F is just simplifying to be z. So that's great. So we have that. And so then if we're calculating the flux of F across the surface, then this would just be equal to the triple integral over G of Z dV. Now, since your solid is a hemisphere, it makes sense that we're going to use what kind of coordinates?
Spherical.
Spherical. And so let's use spherical. And so in spherical, what does the z come out to be in spherical?
Cosine of phi.
Rho cosine phi. And what does dv become in spherical? So we have rho squared sine phi, and then we're going to have d rho, d theta, d phi. And since it's a sphere of radius, what's the radius of the sphere?
2.
2. So the rho is going to go from 0 to 2. And since it's only a half a sphere, if it's a whole sphere, then the phi would go from 0 to pi. But since it's only a half a sphere, the phi is going to go from 0 to
Pi over 2.
pi over 2. And then the theta goes from 0 to 2 pi. All right, so you can see that you could factor this as a function of rho times a function of phi times the function of theta, which would just be the 1. So you're going to have the integral from 0 to 2 pi of 1 d theta times the integral from 0 to pi over 2 of sine phi cosine phi. And then times the integral from 0 to 2 of rho cubed. And so let's go ahead and do this calculation. So this first one's just going to be the length of the interval 2 pi. What's the antiderivative of this guy?
1/2 sine squared phi.
Mm-hmm. And then here we'll have 1/4. Go to the 4th. All right, so with this one, at 0, it's 0. Excuse me, so you're just going to get pi times 1 squared. And then this one is going to be 16 over 4. And that's going to be equal to 4 pi. So, you know, there's not that many surfaces here. There's just the top surface and the bottom surface, but still it's going to be easier to do this problem with the divergence theorem than calculating it directly. So it's going to be much more, probably the integrals involved are going to be more complicated, particularly over that top part than just using the divergence theorem. All right, so you can see that this divergence theorem is a nice shortcut, but let's take a look at one that looks like a really, really tough one. So we're going to evaluate the flux of F across the surface S, where F is equal to 1/2 x squared plus e to the cosine of zy yx plus the ln of z plus 5. And tangent inverse of x times y. So we've got this real kind of crazy vector field there, very complicated. And S is the surface of the solid G bounded by z equals 1 minus x squared, z equals 0, y equals 0, and y plus z equals 2 with outward orientation. All right, so we know we're going to need to calculate, if we're going to use the divergence theorem, we're going to need to calculate the divergence. So let's see what that would be. So if we calculate the divergence of F, let's see, so this is just a function of y and z. So the partial of the first component function with respect to x is just going to be x. So this is just going to be x. And if we look at the second one, the partial of the second component function with respect to y is also going to be x. And then the partial of the z component function with respect to z is 0. So the divergence just came out to be 2x. So even though this thing was very complicated, the divergence is very simple. Now, the solid is a little bit tricky. So we've got this, this guy is a parabolic cylinder. So we're going to have this guy. And then it's being cut off by this plane. The z equals 2 minus x. So this is going to be a plane that's going to cut that off like that. And so just that's a kind of a quick sketch of it. And so we have the z equals 2 minus y. That's the surface right here. We have the z equals 1 minus x squared. That's this surface. And then here, this is going to be your x-axis. Here you're going to have your y-axis. And this is your z-axis. And this is going to cross at 1, 0, 0. All right, so, well, the first thing we need to do is we need to think about calculating a volume integral for this one. So we're going to have the f dot n ds over S is going to be equal to the triple integral over G of the divergence, which is 2x dv. And so let's think about how we could maybe take a slice out of this one. So if I take a slice like this, I can take a slice like that. And I can try and sweep it out with these slices like that. And so let's see how we would do that. So I'm going to have the 2x. And so the first thing I'm going to do is I'm going to integrate with respect to y. So I'm going to do dy. And then the y is going to go from 0. And this one here, we could also think of this as y equal to 2 minus z. That's another way of writing that plane. So we're going to go to from 0 to 2 minus z. So there I'm taking like that. And then the next one is we're going to have dz. And the dz is going to go from z equal to 0 up to z equal to 1 minus x squared. That's right here. And then we're going to do that for each x in between minus 1 and 1. So if you're over here, this would be at minus 1, 0, 0. That's that point right there. And so we're going to do that for each x equal to minus 1 to 1. So that what that means is that we're taking a slice like this and we're moving it all the way from over here to all the way over here. All right, and again, it's not a perfectly drawn sketch. I'm just trying to kind of figure it out from the sketch. It doesn't, not like Disney quality or anything like that up there. All right, so let's first of all integrate with respect to y. So when we integrate with respect to y, we're going to have the integral from minus 1 to 1 and the integral from 0 to 1 minus x squared. And then we're going to have 2xy from 0 to 2 minus z. And then we'll have the dz dx. And so if we put these values in, it's going to be 0 at the lower limit. And so we're going to have the integral from minus 1 to 1. And then we're going to have the integral from 0 to 1 minus x squared of 2x times 2 minus z. And then we're going to integrate this with respect to z. So what we're going to have is we'll have the integral from minus 1 to 1. I'm going to have the 2x, that's a constant. And then we're going to have the 2z minus 1/2 z squared from 0 to 1 minus x squared and dx. And at 0, we're getting 0. So at the 1 minus x squared, let's see what we get. So we're going to have the integral from minus 1 to 1 of 2x, and then we're going to have 2 times 1 minus x squared, and then minus 1/2 of 1 minus x squared. And so what's the answer? If you look at it closely, you should be able to see what the answer is right now.
0?
It's 0. Why is it 0?
Because you end up with odd powers, and when you integrate, you get even powers and they cancel.
Yeah, it's an odd function. So if you look at this part in here, because you have the 1 minus x squared, this is even. And then here you have an odd. And then when you multiply an odd function times an even function, you get an odd function. So the whole thing is odd. And so whenever you have an odd function, and you're integrating the odd function from minus a to a, it's always 0. So this is equal to the integral from -1 to 1 of odd, which is equal to 0. So what this means is that the net flux of F across all of these surfaces, now there's a lot of surfaces here. There's the front surface, the back surface, that parabolic surface, and then the bottom surface. So altogether, how many surfaces do we have? Looks like 4. And to calculate the flux directly would be extremely difficult. But with the divergence theorem, even with this crazy vector field and this kind of complicated solid, we were still able to calculate the flux of it. All right, so one more example that I wanted to show you guys today is just to revisit. This is an example that we did last time. And so you might remember that this was an example that we did in class last time. And so we have these two surfaces. So we have the z equals 0. And then we have the z equals 1 minus x squared minus y squared. And then there's our solid G. And so last time we did this by calculating 2 different surface integrals. But in this case, since the surface does enclose a solid, we can do it with 1 volume integral using the divergence theorem. So I just want to do this problem again, just so that you can compare how much easier it is with the divergence theorem. So if we calculate the divergence of this vector field, what are we going to get? What's the divergence here?
1.
it's going to be 1 because it's going to be 0 plus 1 equals 1. And so our surface integral of f dot n ds just becomes a triple integral, a volume integral of the divergence, which is 1 dv over our solid G. All right, and so this is a nice one for, we can do it with cylindrical. So if we think of this as d, then the d is just going to be equal to the x squared plus y squared less than or equal to 1. That's going to be the projection of our solid on the xy plane. So we can think of it as that integral from 0 to our surface, which is the 1 minus x squared minus y squared of 1 dz, and then dA. And so what we'll have is we'll have the integral over d, and this is going to give me just z from 0 to 1 minus x squared minus y squared. And so we're just going to have the double integral over d of 1 minus x squared minus y squared.
Professor, it froze.
Thank you. So we have that. And then, so after we put it to there, where do we go from here?
Polar coordinates.
Polar coordinates. And we could have, just used the cylindrical coordinates right from the beginning as well. But let's go ahead and do the polar now. So we're going to have the 1 minus r squared. And the dA is the r dr d theta. And then it's a unit disk, so we're going to go from 0 to 1 and 0 to 2 pi. So we're just going to have the integral from 0 to 2 pi of 1 d theta times the integral from 0 to 1 of r minus r cubed dr. And so the first one is just going to be equal to the 2 pi. So we're going to have 2 pi and then 1/2 r squared minus 1/4 r to the 4th from 0 to 1. And so we have 2 pi and then we have 1/2 minus 1/4, which is just 2 pi times a 4th, which is pi over 2, which is the same as we got last time. So the flux of F across both surfaces is pi over 2. And so you can see that I'm putting in a lot of steps. I probably could have done it faster, but you can see that that's going to be an easier way to go with it. Any questions on the divergence theorem? So you can see that it's a nice shortcut. And so I think there's one of these divergence theorem problems on your take home that's due on Friday, in addition to your final that's on Monday. And so you may be able to take what you've done today and do that. So the next thing we're going to talk about is Stoke's theorem. So I at least want to get started with that today. And so let's look at Stoke's theorem. Stoke's theorem, this is your book. And so let's take a look at this. This is Stoke's theorem. So here's what Stoke's theorem says. And basically, Stoke's theorem is kind of like a higher dimensional version of Green's theorem. So remember that Green's theorem gave you a way of transforming a line integral in differential form into a double integral. And what Stoke's theorem does is it gives you a line integral, takes a line integral in space, and it transforms it into a surface integral. So here's what Stoke's theorem says. It says, let S be an oriented, piecewise smooth surface that is bounded by a simple closed, piecewise smooth boundary curve C with positive orientation. And let F be a vector field whose components have continuous partial derivatives on some open region in space that contains S. Then we have this result here, that the line integral over C of F dot dr is equal to the surface integral of the curl of F dot n ds. And so this problem talks about this, the theorem talks about positive orientation. So what is the positive orientation? So let's read up here. Stoke's theorem can be regarded as a higher dimensional version of Green's theorem. Whereas Green's theorem relates a double integral over a plane region D to a line integral around the plane boundary curve, Stoke's theorem relates the surface integral over a surface S to a line integral around the boundary curve of S, which is a space curve. And so so the figure 1 shows an oriented surface S with unit normal n. The orientation of S induces the positive orientation of the boundary curve C. This means that if you walk in the positive direction around C with your head pointing in the direction of the normal, then the surface will always be on your left. So if you look at this picture here, yeah, so you see the little person walking around the boundary curve there. And so there's the boundary curve and then the surface is on the left. And you can see that in this case, when that will be true when the orientation around the curve is counterclockwise. And generally, if we make the orientation along the boundary curve is clockwise, then the man will have to be upside down. Then the positive orientation is downward. So in other words, if the positive orientation is upward, then we have a counterclockwise orientation on the boundary curve. If the positive orientation is downward, if n points down, then the positive direction on the boundary curve is clockwise in that case. So pointing up, counterclockwise, pointing down, clockwise. All right, so we'll talk maybe more next time about why Stoke's theorem works, but right now we don't have too much time. So I just want to go through a few examples of using Stoke's theorem. So this is section 16.8. Take a look at example 1. Oh. Example 1. All right, so we're going to let S be the portion of the paraboloid z equals 4 minus x squared minus y squared, for which z is greater than or equal to 0. and C, the circle x squared plus y squared equal to 4. That forms the boundary of S in the XY plane. And so we're going to verify Stoke's theorem. Assuming that S is orientated upwards, so that C has counterclockwise orientation. All right, so we've got this paraboloid. And here's your C, and we have a counterclockwise orientation on the boundary curve because your normal is pointing up. All right, so what we need to do is we need to find, if we're going to verify Stoke's theorem, we need to find sorry, I didn't finish the problem. So verify Stoke's theorem, assuming that S is oriented upwards, so that C has counterclockwise orientation, and our vector field F is going to be equal to 2z, 3x, and 5y. All right, so so what this means is that I'm going to calculate the line integral around this curve, and then I'm also going to calculate the other one. So so for this curve is a circle of radius 2 with counterclockwise orientation. So we can define C by r of t equal to cosine of 2t as radius 2, and 2 times the sine of t, and then 0. So that's going to be your curve C. And then, so if we have r prime, this is going to be minus 2 sine of t, and then 2 cosine of t, and then 0. And so what we want to do is we want to calculate the integral around our boundary curve C of f dot dr, which is the same thing as the integral from 0 to 2 pi of f of r of t dotted with r prime of t dt. All right, so this is your x, and this is your y. So, and then this is your z. So if I'm going to do the f of r of t, this is going to be equal to the integral from 0 to 2 pi we're going to have the 2z is going to be 2 times 0, that's 0. And then the 3x is going to be 6 cosine t. And then the 5y is going to be 10 sine of t. And then we're going to dot this with r prime, which is the minus 2 sine t, 2 cosine t, and then 0 dt. All right, so when we do the dot product, we'll have 0 times the minus 2 sine, that's 0. We're going to have 2 cosine of t times 6 cosine of t. So we're going to get 12, 0 to 2 pi of cosine squared. And of course, the last one's going to be 0, taking 0 times that. So we're just integrating this guy. And so when we calculate this out, we're going to have 12 over 2. And then we're going to have the integral of 1 plus cosine of 2t. So we have that, so that gives me 6. And then when I integrate it, I'm going to have t plus 1/2 sine of 2t. And at 0, I'm just going to get 0. And so the only thing I'm going to get out of this is when I put the 2 pi in for the t, so I'm going to get 12 pi. And so to verify Stoke's theorem, I need to calculate it the other way. And so remember that Stoke's theorem said that the integral of the curl of f dotted with n ds over s is equal to the line integral around the boundary curve. That's the result of Stoke's theorem. Now remember that the curl of f, you can think of that as the del operator crossed with f. So another way you can state Stoke's theorem that you sometimes see is it's sometimes written like this. It's written as the del cross f dot n ds over s is equal to the line integral on c of f dot dr. So oftentimes you'll see Stoke's theorem written like this. All right, well, we calculated this guy and we found that this was equal to 12 pi. So let's calculate this guy and it should also be equal to 12 pi. And that would verify, at least in this case, that the Stoke's theorem is working just fine. So we need to first of all calculate the curl of f. So the curl of f, which is the same thing as the del cross f, and this is going to give me the I, the J, and the K. And then we'll have our component functions of f, which were 2z, 3x, and 5y. All right, and so let's see what we have for this vector. So we're going to have 5 minus 0, that's 5. And then we're going to have 2 minus 0 is 2. And then for the last one, we're going to have 3 minus 0 is 3. So we have our curl is equal to that. It's this constant vector. All right, now, in this particular case, our our surface here, z is equal to 4 minus x squared minus y squared. And so we're going to have the zx is minus 2x and the zy is equal to minus 2y. And so when we have the curl of f dotted with n ds over s, what this is going to be equal to is we're going to have the curl, which is the 5, 2, 3. And then we're going to dot this on with the 2x and then the 2y and then the 1 dA over d. Because remember, you had the magnitude of this vector is in the denominator, and then the ds, remember, is the magnitude of this vector times dA, and those magnitudes cancel. And in this case, your d is this region here. So you would have the x squared plus y squared less than or equal to 4. That's your d. And so let's see what we have here. So we're going to have the double integral over d. We're going to have 10x plus 4y plus 3 dA. And since we're integrating over this nice polar region, we're going to switch it to polar now. And so when we switch it to polar, we're going to have uh, 10 r cosine theta plus 4 r sine theta plus 3. And then we have the r dr d theta. And the r in this case is going from 0 to 2, because the disk has radius 2 and theta 0 to 2 pi. And so when we need to distribute the r, so we'll have the integral from 0 to 2 pi, and then the integral from 0 to 2, and then we have 10 r cubed, r squared cosine theta, and then plus 4r squared sine theta, and then 3r. So let's do another sheet of paper here. All right, so let's integrate with respect to r first. So we're going to have the integral from 0 to 2 pi. And then integrating with respect to r, I'm going to get 10r cubed over 3. And then here I'm going to have 4/3 r cubed sine theta, and then 3 over 2 r squared from 0 to 2. And everything's going to be 0 at the lower limit. So let's see what we get at the upper limit. So at the upper limit, we're going to have 8 times 10 is 80 over 3. So we have 80 over 3 cosine of theta. And then here we're going to have 8 times 4 is 32 over 3 sine theta. And then for this one, we're going to have 3 over 2 times 4, which is going to give me just 6. And so let's just go ahead and integrate this now. So we're going to have 80 over 3 sine theta, and then minus 32 over 3 cosine theta, and then 6 theta. And then we go from 0 to 2 pi. So we're going to have 80 over 3 times sine of 2 pi minus sine of 0. Both of those guys are 0. And then we're going to have minus 32 over 3 times cosine of 2 pi minus cosine of 0. So that's going to be 1 minus 1, which is 0. And then we're going to have 6 times 2 pi minus 0. So we have 80 over 3 times 0 minus 32 over 3 times 0 plus 12 pi equals 12 pi. So the Stokes theorem appears to work just fine. All right, so I'm going to take a break for a while, and then I'm going to come back. Maybe I'll do a couple more examples on this recording. Okay, so suppose S1 and S2 are surfaces with the same positively oriented boundary curve C, and F is any vector field that satisfies the hypotheses of Stokes' theorem. Then by Stokes' theorem, we would have the curl of F dot n ds over S1 would be equal to this line integral around the boundary curve C. And that would also be equal to the curl of F dot n ds over this other surface. So because they're both equal to the line integral, we're getting the same value. So in some sense, if it has the same boundary curve, it's independent of the surface that has that boundary curve. You could think of it like that. So for example, if we let S2 be the upper hemisphere of x squared plus y squared plus z squared equals 4, so that would mean that z is equal to the square root of 4 minus x squared minus y squared, then the boundary curve would be the same as in the first example that we looked at. It would be x squared plus y squared equals 4, just like in the first example. So then we would have S2 would be the upper hemisphere, whereas in example 1, we had the parabola. So in the example that we looked at in example 1, this was, remember, the z was equal to 4 minus x squared minus y squared, and would have the boundary curve x squared plus y squared equals 4. Whereas here we have z equal to the square root of 4 minus x squared minus y squared. And that would still have that same boundary curve, x squared plus y squared equals 4. So that would mean that these two surface integrals, the curl of f dot n ds over S2 and over S1 are equal because they're both equal to this line integral. So in some sense, you could say that if the boundary curve is the same, then it's sort of independent of the surface that has that boundary curve, assuming that the hypotheses of Stokes' theorem are satisfied. All right, so let's take a look at one more example today. Next time, we'll look at sort of physically what the Stokes' theorem represents, and you'll get a better idea as to why this is true when we have more time to talk about that next time. So for our last example today, we're going to look at this example 2 here. So we're going to let C be the rectangle in the plane z equals y that lies over r equal to 0, 1, cross 0, 3. So this is going to be your x-axis. And then here we have the y-axis there. Such that looking down on the rectangle, there's a clockwise orientation. So you can see that if we were to look down on it, we would have a clockwise orientation. And then we're going to find the line integral of f around c. Now, we could do this directly. We could parameterize each of these 4 segments, but then we would have to calculate 4 different line integrals to calculate that. That's going to be a lot of work. So instead of doing that, we're going to need to calculate one surface integral. And so by Stoke's theorem, this would be equal to the double integral over S of the curl of f dot n ds. And so we would prefer to calculate that because that's going to be less work than doing 4 individual line integrals. We'd have to figure out how to parameterize that and then do all those calculations. That's going to be quite a bit of work there. All right, so the first thing we need to do is we need to calculate the curl. So for our curl, the curl of f, remember that's equal to the del cross f. And so we're going to have the I, the j, and the k. And we'll have our partial derivatives. And then in the bottom row, we're going to put the component functions of f. So we'll have the x squared, the 4x, y cubed, and then the y squared x. And so the curl of f, so first of all, we're going to get 2yx. So we have 2yx, and then we're going to have 0 minus y squared. And for this last one, we're going to have 4y cubed minus 0. So we have that. So that's my curl. Now, my surface in this case, my surface is z equal to y. So normally, I might take minus zx and minus zy, and then 1. But the problem with that is that this is pointing up. This vector would point up. And so that would give you a vector normal that would point up like that. But because we have a clockwise orientation, that means that our normal has to point down. If our orientation was clockwise, counterclockwise looking above, then we would take a normal that points up. So what we need to do is we need to reverse the orientation. So instead of this one, we're going to take this one. We're going to take zx, zy, and minus 1. So we're going to take that, since the orientation around C is clockwise. So that means that we need the normal to point down. So in this case, what we're going to get here is the zx is going to be 0, and the zy is 1, and then we're going to have minus 1. All right, so if we look at, so So then our line integral that's going to be equal to the surface integral. We're going to have the curl of f dot n ds. And remember that there's a magnitude that cancels there. So we're going to have this divided by its magnitude multiplied by the magnitude times dA. Those magnitudes cancel. So we're just going to have the curl dotted on with this guy. So this is going to be equal to the double integral over r. And then we're going to have our curl, which is the 2yx, and then minus y squared, 4y cubed. And we're going to dot that with 0, 1, minus 1, dA. So we have that. And then, so when we do that dot product, we're going to have minus y squared, because the first component function is multiplied by 0. So we just get the minus y squared and then minus 4y cubed. dA. And so we can write this as the integral from 0 to 1, and then the integral from 0 to 3. So we have minus y squared minus 4y cubed dy, and then dx. And so if we integrate, we can split this up as a product. So we can write it as the product from 0 to 1 of 1 dx, which is just going to be 1 times the integral from 0 to 3 of minus y squared minus 4y cubed dy. And this first one is just going to be 1. So we're just going to get this one. So I'm going to get minus 1/3 y cubed minus y to the 4th from 0 to 3. And so everything's going to be 0 at that lower limit. So we'll just get a 0 there. So we'll end up with minus 27 over 3 minus 81, which is going to be minus 9 minus 81 equals minus 90. And that's it. So to evaluate the integral of f dot dr directly, would require 4 separate integrations. But using Stoke's theorem, we can evaluate using only one surface integral. All right. That's it for today. Have a good day.